All right, welcome back. And our next speaker this morning is Daniel Sutherland, Associate Professor of Philosophy at the University of Illinois at Chicago. Daniel did his PhD at UCLA, but was a visiting professor at Harvard about 6 years ago. I won't belabor the metaphor of yet another star in the constellation, but certainly one of the linchpins of the young group of scholars in Kant's philosophy of mathematics. His publications recently include Kant's philosophy of mathematics in the Greek mathematical tradition, the role of magnitude in Kant's critical philosophy, Kant and arithmetic and algebra, and the theory of proportions, from Kant to Frege, number, pure units, and the limits of conceptual representation, philosophy and geometrical practice in Leibniz, Wolff, and the early Kant. We know from the discussions this morning how central Daniel's ideas about Kant and the concept of number are and have been among the people working on Kant's philosophy of mathematics, and indeed his topic this morning is Kant's conception of number.
Thank you very much. I want to thank all those who helped make this possible. I'm very pleased to be able to be here. I want to especially thank Oprah for making this possible. I wouldn't have missed it for the world. This paper, I wish I had titled it properly and followed the example of Emily and Oprah. It should have been, quote, Kant's philosophy of arithmetic, close quote, and Kant's conception of number, because the considerations that come up in this paper first came up in that classic article of Charles's, and I will refer to it in the paper. But I think it's clear from previous comments, our intellectual debt to Charles is considerable. And what's interesting is that an article from 1969, which contributed with Jakob Hintiger's work to this renaissance in studying Kant's philosophy of mathematics, not only generated so much interest and work following it, including Michael Friedman's and others, but that going back to it, 2014, going back to this 1969 article, it's still bearing fruit, at least for me, as well as his other articles. So this talk is called Kant's Conception of Number. Some of you may recognize the theme. This is, I've been fortunate enough to be here for now the fourth time in the last 5 years, all pursuing this same topic. I hope to have reached some conclusions finally, but it's a pleasure for that reason to give the talk here. When I came and gave the talk, that was the beginning of a project. It was also 6 weeks after my son was born, and it was shortly after Obama was inaugurated. I wish I'd been able to make as rapid a progress as my son has in the last 5 years. Or maybe I've made a bit more progress than Obama. Maybe that's because as hard as Kant is, he's not as bad as Congress. So, my paper will be very different from the two previous papers in ways that will be quite obvious, but I will have to underline a few of them. Most investigations of Kant's philosophy of arithmetic quite reasonably focus on those passages in which Kant argues for the role of intuition and infer what Kant's conception of number is, and in particular whether Kant holds a conception of number that is fundamentally cardinal or ordinal. I would like to reverse this approach. To the extent possible, I would like to first determine what Kant's conception of number is, and only then consider the role of intuition in arithmetical cognition. I say to the extent possible, since Kant's own emphasis is on intuition. Doing so will give us a much better idea of what role intuition is called on to play in arithmetical cognition. In fact, it will allow us to break through an interpretive impasse I will describe below. So my thesis is as follows. I will focus on Kant's views during the time of the critique of pure reason. So I'm expressly not considering the question that Emily was tackling about the stability of Kant's views and the development of Kant's views. I'm just looking at the critical period. And this is specifically in response to the same comments of Charles's in arithmetic of the categories. I will argue that Kant's concern with explaining arithmetical cognition leads him to focus on enumeration, and that, to the extent that it can be settled, his account includes both cardinal and ordinal elements. More specifically, I will argue that Kant's conception of number in general is cardinal, but that ordinal elements play a central role in contributing to the exact representation of particular cardinals, as well as to measurement, and are also included in his conception of number. The position I argue for vindicates and reconciles recent interpretations that have emphasized either cardinal or ordinal aspects of Kant's views, and puts us in a position in future work to determine and critically assess the particular roles that Kant claims for time and space in arithmetical cognition. Just a few clarifications. I say Kant's conception of number rather than Kant's concept of number, because I'm trying to ask this question about how he's thinking about number in a very general way, before asking about how to understand the contributions of intuition on the one hand or the categories on the other to give a representation of number. That's part of what I want to put off until later to the extent possible. Now, we'll be taking a broad perspective, examining the relations among traditional Kantian and contemporary accounts of cardinality and ordinality. Drawing out what they have in common without being anachronistic requires not importing all the sophistication of our modern understanding. For example, the set membership relation was not articulated in Kant's time and was not clearly distinguished from part-whole relations. I will use the term collection as an umbrella notion that covers both a rudimentary understanding that does not distinguish the set membership relation from the part-whole relation and our modern notion of set. I will use individual for either an individual considered on its own, an individual in a collection, or an element of a set. Finally, no one in Kant's day had anything like our well-developed theory of the infinite. In all that follows, we will only be considering indefinitely large but finite collections and numbers, even when considering modern accounts. Now, for those who are interested in foundations of mathematics, that robs the distinction between cardinality and ordinality of what seems to be their clearest distinction in the infinite. But there it is. Kant didn't have the theory of the infinite, and we're trying to bring things down to understand his views. So the structure of the paper is as follows. Part 2 provides background and criteria to assess Kant's views. Part 3 turns to evidence from the time of the critique of pure reason, and Part 4 then considers a serious challenge informed by our modern understanding of the cardinals, responding to which prompts important further elaboration of Kant's views. Okay, so now I'm on to section 2, background on cardinality and ordinality. This would be very compressed. In the Greek mathematical tradition, numbers were tied to questions of size. That is, they were employed in answer to the question how big something is. The question took two forms. For continuous magnitudes, the question was how much, while for collections, the question was how many. The connection between numbers and collections of individuals was quite tight. The core notion was that of the size of the collection. And this is also in Euclid in his definition of numbers in the elements. The cardinal was the dominant understanding of number down to Kant's time, and in Kant's immediate predecessors as well, such as Wolff, Kestner, Carstens, and Zegner. In contrast, and quite strikingly, ordinality as a notion of number was not really developed at all. As late as the 18th century, in fact, ordinal was a lexical term. That is, ordinal was used to refer to, in the first instances, to adjectives, first, second, and third, and so on, used to order items. Of course, you can also use 1, 2, 3 to order items, but what's interesting is if you look for ordinality in German dictionaries of the time, they just make it sound as if it's a grammatical distinction. The core notion at the basis of ordinality, expressed in modern terms, is nevertheless a strict linear ordering of discrete individuals beginning with an initial individual. I won't say much about the modern conception of cardinality and ordinality to this audience, other than to note that they can be seen as developing the core traditional notions. The key notion underlying the cardinal conception is not size itself, but sameness of size, or equinumerosity, which is explained as the existence of a 1-1 onto function from the individuals of one collection to the individuals of another, while the fundamental notion underlying modern accounts of the ordinals is the successor function, a discrete function that for the finite ordinals can be thought of as iterated indefinitely. Now, for Kant. Since the cardinal conception of number held pride of place from at least Euclid up to Kant's contemporaries, and there was little or no theory of ordinals at that time, one might be inclined to think that Kant's views are continuous with the traditional cardinal conception. In fact, Kant directly connects his views with traditional accounts of cardinal number when he explains magnitudes understood as quantitas or quantity to be an answer to the question how big something is, or wie groß etwas sei. That's in B204 in the Axioms of Intuition. Kant illustrates his point with examples from arithmetic, which is evidence that he has not only continuous but also discrete magnitudes in mind. Kant's theory of magnitudes provides further support for a cardinal interpretation, a theory that promises a unified account of arithmetic, algebra, and geometry, as well as a common role for intuition. So, in fact, my tendency toward a cardinal interpretation of Kant's philosophy of mathematics started because I was trying to figure out Kant's theory of magnitudes, and that seemed to push toward, in my view, seemed to push toward a cardinal view of number. There is much else besides which suggests that Kant has a cardinal conception of number. So in summary, there are good historical, textual, and systematic reasons for thinking that Kant held the cardinal conception of number. One could, however, take quite a different perspective of Kant's relation to the tradition and to his immediate predecessors. Kant may connect what he says about number with the dominant understanding of his day, but he also emphasizes succession and the role of time, which are almost entirely absent in his immediate predecessors. And it's really striking. So I was looking for understanding Kant's views by understanding the views current at the time. When you read them, I think, oh yeah, cardinality is what's in the air, but then you read Kant, and what's striking is how different his account is, and his emphasis on succession. In fact, in places, Kant focuses almost exclusively on the successiveness of enumeration and the role of time, so that it can seem that the crucial notion underlying number representation is successive iteration. So Charles Parsons, in his classic article, Kant's Philosophy of Arithmetic, brings this aspect of Kant's views to the fore to explain the special connection between arithmetic and time. You can see number one in the handout if you'd like. There's a couple of quotes there. He states that time enters in the succession of mental acts of running through a group of n objects as in counting, adding that in the operations involved in representing a number to the senses, we also generate a structure in time, which represents the number. Time provides a universal source of models for the numbers. And there's much more from that page of Kant's Philosophy of Arithmetic that is of great value, and I just can't discuss it all. And in Arithmetic and the Categories, another tremendous article, I think, that has somewhat been neglected, Parsons explicitly connects this to the representation of iteration and an ordinal conception of number. He points out that the role of time in representing successive iteration corresponds to the more abstract notion of finite iteration, in terms of which finite ordinals are often explained. In Kant and the Exact Sciences, Michael Friedman expands and modifies Parsons' suggestion and presses a solely ordinal interpretation, disavowing a cardinal element in Kant's conception of number. And there's a lot to say about how Michael develops this view and how he also disagrees with Charles, but I will simply do not have time to go into it. And I also think that one has to be careful to qualify the sense in which Mike was pushing forward a solely ordinal interpretation. Nevertheless, I did put a few quotes on the handout in which he emphasizes or wants to say that Kant doesn't have a cardinal conception of number in a way that I actually had thought he did have, Kant had. And Friedman cites a good deal of textual evidence for his interpretation, and there are important philosophical advantages as well that I don't have time to recount. That has to do with the status of mathematical objects, whether you can get away from the commitment to mathematical objects, and how to deal with the problem of generalizing from particular intuition. So there's a lot in favor of that interpretation. Here it is. I did say there's some vindication at the end. So, faced with evidence on both sides, one might wish to conclude that Kant's views include elements of both. But this oversimplifies the interpretive challenge we face. But the evidence I've referred to leaves open the possibility that, even if Kant does not expressly say so, Kant's conception of number is exclusively cardinal, and that the passages that emphasize succession and the role of time point to what are, in Kant's view, necessary conditions for arithmetical cognition, but are not incorporated into his conception of number. But what's good for the goose is good for the gander. One could also argue that the texts that focus on succession and the role of time get at the heart of Kant's conception of number, and apparent cardinal elements are mere aids, or at most necessary conditions for arithmetical cognition. So that's the impasse that I set up 5 years ago and articulated, and now I'm going to try to break through the impasse. Any attempt, so I'm now on to section 3 here. Any attempt to relate Kant's views of cardinality and ordinality to our contemporary understanding of them must be sensitive to broad differences in approach. Kant's aims not to provide a foundation for arithmetic in terms of more basic logical relations, but to provide a foundation for arithmetical cognition in the following sense. Arithmetical cognition in mathematics and even in straightforward application of numbers to individuals and collections is a complex cognitive achievement whose possibility Kant attempts to explain in terms of our more basic cognitive resources. Now, the two kinds of foundational project are closely related and influence each other. I don't want to downplay that at all. It's not as if later foundations of arithmetic did not care about epistemology, or obviously not. But the difference, or cognition, or how we represent, but the difference nevertheless has important consequences. One is that our contemporary foundations of arithmetic strives for simplicity and strives to avoid redundancy. In contrast, an account of arithmetical cognition begins with whatever cognitive capacities we have. If those capacities gave us the resources to represent, for example, both the successor function and one-to-one correspondence, then there would be no reason the account could not or should not appeal to both. Second, foundations of arithmetic may account for the logical structure and presuppositions of the natural numbers, setting aside specific requirements for our representing the natural numbers. For example, the foundations of arithmetic will have something to say what being a particular number, such as 34, consists in, but may abstract from the conditions required for our representing 34, rather than 35 or 33. In contrast, an account of arithmetical cognition will see its central task, or one of its central tasks, is explaining how our basic cognitive resources make arithmetical representations and cognitions possible. This is all preparatory. Now, on section 4, criterial differences between cardinality and ordinality. The way that numbers are related to individuals provides the first method of hoping to determine the conception of number Kant employs. When a cardinal number is applied, it is predicated either of a collection or a plurality of individual elements, while an ordinal number is predicated of an individual element. The former insofar as the plurality of elements constitute a collection, the latter insofar as an individual element stands in an order, or an ordering. The sentence, "There are 5 kiwis on the table," is about the collection of kiwis that the plurality of kiwis constitute. On the other hand, the sentence, "That's the 6th kiwi," the term 6 is applied to just one individual kiwi. So I'm going to call that the collection criterion. Matters are complicated, however, since it is possible to use an ordinal number to measure the size of the collection. One might think that what one represents in thinking that the size of the collection is 6 is that the ordinal number 6 measures the size of the collection. That is, were the collection enumerated, the ordinal 6 would be applied to the last individual enumerated. Thus, the reference to a collection all by itself does not show that the conception is cardinal. Second criterion. I will call the second possible criterion the ordering criterion. As discussed in the first section, on an ordinal conception, ordering is fundamental. For cardinal elements, in contrast, the notion of size is fundamental, and the ordering of the cardinals depends on the relations between the sizes. So that, for example, in Frege's account. More specifically, if we're translating back into Kant's time before a way of logically and theoretically being able to articulate the order relation, one cardinal is less than another if a collection corresponding to the first is equal in size to a proper part of the second. The way Kant discusses ordering can therefore provide evidence for his underlying conception of number. Here as well, some care is needed. A reference to ordering and even an emphasis on ordering will not necessarily indicate that ordering is taken as fundamental, since it might simply omit to give an account of what grounds the ordering. If the fact that one number is greater than another is explained in terms of the relation between the corresponding collections, for example, that the size of one collection is equal to a proper part of another collection, that would be a good indication of the cardinal conception of number. What I will call the addition criterion provides a third way to distinguish cardinal and ordinal elements in Kant's view. Cardinal addition can be construed as, or it is at least exemplified by, the combining in thought of disjoint collections, such as 3 kiwis and 4 nashi. In contrast, adding one ordinal to another can be construed as, or is at least exemplified by, a simple concatenation of orderings determining the final position. For example, the third person in line after the fourth person is naturally understood as a continuation of the ordering up to the fourth by further ordering up to the third to arrive at the seventh person in line. There are complications with applying these criteria, and I'm sort of simplifying and boiling some things out. And nevertheless, I think these criteria at least offer the best hope for trying to figure out what Kant's conception of number is. But they are particularly difficult to apply because cardinals and ordinals are closely intertwined in enumeration, to which I want to now turn. So I'm in section 5. It is one thing to have a general conception of number that is connected to sizes of collections or is related to a position in an ordering. It is quite another to account for the representation of particular cardinals or ordinals, such as 25 or the 25th, which complicates matters considerably. It is a fundamental feature of human arithmetical cognition that reliably determining the exact size of a collection when it contains more than about 5 individuals requires enumeration. And that in turn requires considering the elements successively and imposing an ordering on them, which are hallmarks of an ordinal conception of number. So as an aside, I should say that neither I nor Kant is interested in any particular limit there might be here. What's important is there is a limit, and the kind of conception of number Kant wishes to explain, which is that which can be used in mathematics and so on. There will be no limit to the numbers, so the fact that there is a limit is all that's needed. The fact that the limit is rather low just makes the limitation rather salient. One must be quite careful, however, for the underlying conception of number and the procedure of enumerating are distinct. And it is unclear what sort of cognition or representation is indicated by a particular case of enumeration. For example, at each assignment of a numeral n, one might represent that this is the next in an ordering. On the other hand, one might be representing that we now have a collection of size n of individuals counted so far. This is Charles has some helpful discussions of ways of thinking about these things in mathematical thought and its objects, particularly section 32. In fact, it is possible to enumerate quite absent-mindedly, in the sense of relying on mere rote memory of the numerals and the algorithm of unique numeral assignment, a procedure that can be nearly automatic. The point is that the reliance on the act or procedure of enumeration does not itself dictate what conception of number we are employing. This is a crucial point for our inquiry. One cannot simply take Kant's references to enumeration as evidence that his conception of number is solely cardinal. What I have said about the role of enumeration in the exact representation of particular cardinals may seem to leave us with an unstable account. If judging that there are 17 horses in a field rather than 16 or 18 implicitly relies on the possibility of imposing a strict linear ordering on the horses, in what sense are we representing cardinality? There are, I believe, 3 aspects of the representation of a particular cardinal that need to be distinguished. First, that we're representing the size of a collection. Second, that we're representing that the collection has an exact size. Finally, we're representing that were we to enumerate the individuals in the collection, we would reach the numeral 17 in our numeral system. As an aside, I'd say that one might worry that this appeal to a numeral in a numeral system assumes that it's what we're trying to explain. I don't think so, but I don't have time to defend the claim now. I also want to say that proportion is something that I am setting aside for now, but relates directly to Oprah's work, and I have gained a lot of insight from her work, and I will continue to. But again, setting that aside. Now, the first two aspects, that is a representation of the size of the collection, and furthermore, representing that the collection has an exact size, would be sufficient to establish that the conception of number in general employed includes cardinal elements. Furthermore, the conception of number could even be construed as exclusively cardinal if the third aspect is regarded as a mere necessary condition for the exact specification of the particular size of the cardinal. So I think this is the view I had prior to 5 years ago. You got a cardinal conception of number, and yeah, I know you have to count them, but we're just limited human beings, and well, what the conception of number is of the size of the collection and is cardinal. All right, so now I'd like to turn to talk about some texts, and I've given you quite a few on the handout. I'm not going to be able to read through them, and a lot of what I'm going to do is sort of summarize ways of thinking about these texts. I'm going to spend more time on the D1516 passage and the schematism than other passages. But what I say there demonstrates a lot of how I approach the text and other texts, and I'll just summarize the results. I will only discuss the second part of the three-part passage at B1516 because it gives Kant's positive view and because I don't have a great deal of time. Kant appeals to enumeration here to make his argument that this proposition relies on intuition. He takes the fingers of his hand corresponding to the number 5 to assist in adding units of the 5 one after another. On its own, this could be taken to suggest an ordinal understanding of addition in which the fingers aid in representing the ordering of the ordinals. That is, I count from the 7th to the 12th, one by one, and use my fingers to keep track of having done so 5 times. So the idea is you simply, as an aid here, is, you know, I could say, I'm starting with 7, 1 is 8, 2 is 9, 3 is 10, 11, and I made a mistake. So use your hand and that'll help you, right? 5, 6, 7, 8, well, anyway. It's going to help. The key move here is, as I pointed out, however, all right, so there's a key move that I want to make at this point, however. The process of enumeration is not by itself sufficient to show that the conception of number employed is solely ordinal. For all that has been said so far, in fact, it could even be cardinal, one might have in mind a collection of 7 and represent adding 1 to get a collection of 8, 1 more to get a collection of 9, and so on up to a collection of 12. In which case the underlying conception of number would be cardinal. On the other hand, there's a nearly comical difficulty with taking Kant's example as a straightforward representation of the sum of 2 cardinals. Namely, Kant has chosen an example in which it is impossible to represent the sum with the fingers of 2 hands. Hence, he does not appear to be interested in representing the collection corresponding to the sum. This might push one back in the direction of an ordinal interpretation. I don't really think this is a difficulty for a cardinal interpretation, however. As I noted above, it would be wrong to assume that the exact representation of each cardinal number requires that it be represented by a collection of the corresponding size. The representation of cardinals 7, 5, or 12 need only contain the thought of the exact size of a collection in general, together with the thought that the size is or can be determined through enumeration up to the corresponding numeral. It would be a mistake to hold that, if Kant held a cardinal conception, that he thinks each and every cardinal must be represented by a corresponding collection. This fact is obscured by the fact, of course, that he's referring to the 5 fingers on the hand. There is further evidence that Kant's underlying conception of number includes cardinal elements. Now, I'm not arguing that it's exclusively cardinal, but there are cardinal elements floating around in here. I only have time to quickly summarize the evidence here. First, Kant states that I add the units that I previously took together in order to constitute the number 5. In other words, he first takes the units represented by the fingers together to represent the number 5. So he first takes the, takes the numbers, fingers together to constitute the number 5, and then, so he's identifying 2 different steps there, then I enumerate the 5, which suggests that my starting point before enumerating the 12 is to take the 5 fingers together as a collection to represent the number 5. Second, if you had a solely ordinal conception on which the ordinals are used to measure the size of a collection, then the last ordinal reached is taken to represent the size of the collection. The transitioning from reaching the last ordinal, the 12th, right, applied to an individual in an ordering, in this case the 12th, and taking that ordinal to reflect the size of the entire collection is a significant step. Right? There's an important difference there. If Kant has a solely ordinal conception of number, this step calls for particular attention and emphasis. Third, Kant refers to taking together of units represented by fingers, not, say, a taking together of instances of the operation of adding in time. So he talks about one after the other, but he talks about the fingers. Fourth, Kant refers to the image of the concept of 5, for he says, with regard to that image of mine, and the most natural reading of image is that all 5 fingers on the hand together provide that image. Fifth, and finally, Kant states that one must go beyond the concept, seeking assistance in the intuition that corresponds to one of the two one's 5 fingers say, or as Zegner in his arithmetic, 5 points. Kant is referring to Zegner's mathematical text, which is significant because, as I mentioned in section 2.1, Zegner has a cardinal conception of number. Now, that was scattershot, five further reasons for thinking there are at least cardinal elements in Kant's conception of numbers. And one might argue that at least for the first 4 of the points mentioned, one cannot rule out the ordinal reading. So, for example, Mark van Atten was pushing me on the first point about the 5 fingers constituting the 5. Why does that have to be cardinal? And, for example, then, one could look for a different reading of image. This is an interesting suggestion. It's one of the reasons I put the second quote from Friedman on the handout, because he says exactly this, suggesting that rather than think of image in the natural way as being some sort of visual image, we have a broader notion of image that includes something that's simply represented in time, so that something represented in time alone could be an image in Kant. And that actually sounds Kantian in a way, like that Kant would extend that. So that's one of the reasons I put that quote on. So I think you could push against each of these. But even if you pushed against all these points, they are strong indicators that Kant's conception is not solely ordinal, but includes cardinal elements. For if Kant had wished to introduce a new, solely ordinal understanding of number that departed from his immediate and well-known predecessors, such as Zegner, he would have underscored how his understanding differs from the cardinal reading. And these are all sort of taken prima facie, it sounds cardinal. So I want to go now to the schematism passage. And that's 4 on the handout. Kant is clearly highlighting here the role of successiveness in the act of addition, where in this case the addition is not of 2 distinct numbers, but the addition of unit to unit and the representation of number. Moreover, anticipating now a specific role for intuition, Kant clearly thinks that time plays a role in representing successive addition, and of course the moments of time form a strict linear ordering with an initial element. In an application. I believe that the schematism passage provides clear evidence of ordinal elements in Kant's account of arithmetical cognition. I'm not going to argue for that since I think that's sort of been the dominant view. But nor do I think that one could reasonably argue, and this is now I'm differing with my former self, one could reasonably argue that these ordinal features are merely necessary conditions and deny that they are incorporated into Kant's conception of number. For Kant explicitly identifies number with the schema of magnitude as a concept of the understanding. Now, while it is unclear how exactly to understand the schema as a concept of the understanding, it remains that number, a representation which summarizes successive addition, is identified with the schema of magnitude as a concept of the understanding, strongly suggesting that successive addition is somehow part of Kant's conception of number.
So are you meaning this to say that it's number that's a concept of the understanding, not that magnitude is a concept of the understanding?
No, magnitude is a concept of the understanding.
Are you saying that this is also saying that number is?
Number is the schema of magnitude as the concept of it. Yeah. No, sorry. Yeah. So other texts. I will not have time to discuss the other texts, so let me just quickly summarize. And again, I have them on the handout, and I'm happy to discuss them later. And those are 5 through 8 on the handout. In the Axioms of Intuition, Kant draws a distinction between representing the composition of 7 and 5 and the thought of their addition, indicating that the former is richer than the latter. So one might hope to use the addition criterion to get some evidence here. Unfortunately, Kant does not clarify what he means by the distinction in the passage, so we're left at 6s and 7s. But more can be said about it when we take into account his theory of magnitude below. The Phenomena Numina text which refers to fingers, beads of an abacus, or strokes and points placed before the eyes, might seem to support a cardinal reading. But I think on careful consideration, it doesn't provide good evidence one way or the other. I used to think it was, look, there's a collection, right? But I think it's not so clear. The discipline of pure reason, one might hope, would tell us a great deal, contrasting philosophical and mathematical method as it does, but it only mentions arithmetic once, and it does not shed light on Kant's view of number. On the other hand, in section 10 of Prolegomena at 4.283, we find support for the idea that the inclusion of ordinal elements in this conception of number, for Kant states, even arithmetic brings about its numbered concepts through successive setting out of units of time. So this echoes the schematism, but is more committal to, he's talking about the numbered concepts themselves and how they are brought about. Finally, in a letter to Schultz in November of 1788, Kant refers to bringing forth a number. He emphasizes the act of succession and does not mention spatial representation of units. Finally, and this is significant for the addition criteria, he states that the successive addition is only employed as a continuation of the counting of the number 3, which certainly sounds like an ordinal conception of addition. So to summarize my reading of the text, I think that the text indicates that Kant had a conception of number that included both cardinal and ordinal elements. More specifically, Kant's conception of number in general is based on the idea of the exact size of a collection of individuals, and hence reflects the cardinal conception of number. At the same time, Kant is sensitive to the fact that the exact representation of particular cardinal numbers requires enumeration in a way that his immediate predecessors were not sensitive to, and this leads Kant to incorporate ordinal elements into his conception of number. Now, I do not claim that Kant had the distinction between a conception of number in general and the exact representation of particular cardinals firmly in mind, or that one includes cardinal elements and the other ordinal. I only claim that we can find evidence of both, and that it is the best interpretation of the roles they play that fits the evidence. Despite what I said, one might be convinced of the ordinal elements in Kant's views while hoping for stronger evidence for the claim that Kant's conception of number in general is cardinal. Kant's theory of magnitude provides that evidence. Now on to section 7. If Kant thinks of the employment of the categories of quantity in the case of discrete magnitudes in anything like the way he thinks of their use in representing continuous magnitudes, and I think he does, then the natural interpretation is that we cognize discrete magnitudes and their collection by cognizing the individuals under the categories of unity, plurality, and totality, and the collection of individuals under the category of allness. Such a representation of a collection would form the basis of a cardinal representation of number. At the same time, it is only the basis, for it is one thing to represent a collection. It is quite a bit more to represent its particular size, or even that it has a particular size, a point to which we'll return shortly after we consider another passage from the Prolegomena. Now, the Prolegomena presentation of the categories seems to point to a use of the categories of quantity in an ordinal conception of number. That's 9 on the handout. The unity mentioned here is not simply the unity of an individual, but the unity of a unit of measure. For continuous magnitudes, a unit is chosen and then the unit is used to measure the plurality of units up to the totality of units found in that magnitude. For example, in taking some specified line segment as a unit to measure the length of another line segment. One could take the same sort of measurement view for discrete magnitudes, where in this case, a specification of the unit would be a specification of what counts as what you're counting, gloves or pairs of gloves, for example. And what is measured is the size of the collection. That is, the categories of quantity are employed for the ordinal elements required for the exact representation of a particular cardinal. But this seems to open up the possibility that Kant's conception of number is solely ordinal after all. In the following way, the categories of quantity are employed in the representation of individuals and collections, but they are not representations of number. Then, these same categories are now employed in measuring and exactly representing the particular sizes of collections, and it is only at this point that representations of number arise. So for further evidence on this issue, let's turn to the second criteria, ordering. Again, in the context of this theory of magnitude. So I've just raised a problem for thinking that Kant has a mixed conception rather than solely ordinal. I'm going to hold off for a second. Now, on an ordinal conception of number, to say that one number is greater than another is simply to say that it appears later in a strict linear ordering. On a cardinal conception of number, in contrast, ordering can be represented by means of the part-whole relations of the parts of a collection. More specifically, the greater than relation can be represented as the part-whole relations within a collection, so that the two of a collection of three can be regarded as a part of the whole collection. The notion of equinumerosity allows, then, the ordering of sizes of disjoint collections. And I will say more about equinumerosity in section 8 below. For an ordering based on the part-whole relations of collections, greater than means not just later in an ordering, but more than, insofar as the larger collection includes the smaller, or a part equinumerous with the smaller, and still more individuals. The evidence from Kant's general theory of magnitudes points to a cardinal conception of ordering. In short, in lecture notes, Kant consistently defines the notion of larger or greater than and the notion of less than in terms of the part-whole relation and equality. And that's number 10 on the handout. One might think that Kant only means larger than here, and that he doesn't, rather than greater than, and that he doesn't have the specifically mathematical notion in mind. However, in a subsequent lecture note that dates from the late 1780s, he puts the point explicitly in terms of greater than and less than, employing the mathematical symbols for them. So that's number 11 on the handout. Greater than and less than are defined in terms of the part-whole relation and equality. Kant understands part in the sense of a proper part, and by definition, the whole is greater than the part. In fact, in the introduction to the Critique of Pure Reason, Kant states that these propositions are analytic and play a role in mathematics. That's number 12 on the handout. Kant has a specifically mathematical understanding of this principle in this context, even using the greater than symbol to express the proposition. The upshot is that Kant's understanding of the mathematical relations of greater than and less than for discrete magnitudes is a difference in the size of collections of individuals. In contrast, I'm aware of no evidence that Kant explains or understands greater than and less than as expressing only relative position in a strict linear ordering. This is a striking result, since we have seen that Kant appeals to enumeration for the exact representation of particular cardinal numbers, and for this role, a mere strict linear ordering is essential. Thus, both sorts of ordering are included in his conception of number. This would be a defect in a foundation for arithmetic, but as I noted in section 2 above, Kant's aim is to explain the possibility of arithmetical cognition in terms of our basic cognitive resources. And if arithmetical cognition employs both notions of ordering, it is no defect to include both. At the same time, we have not yet explained how, on Kant's view, the categories of quantity applied to individuals and collections moves beyond the mere representation of collections to a representation of number or the size of a collection. I will return to this issue shortly. I don't have time to go into the details here about theory of magnitudes and the addition criterion, but there's some evidence that Kant thinks of addition as aggregation, where that is a union of disjoint collections rather than concatenation of ordering. So that's number 13 on the handout. But that depends on the etymology of the word aggregation here. I'm assuming that Kant is using the word in a different way. That is its original meaning, is a gathering together of collections. But on the other hand, we saw in the Schultz letter comes very close to describing addition as a concatenation of orderings. So I think the evidence is conflicting there, and this is a point at which Kant may not have a determinate view or worked out view completely. To sum up, Kant's theory of magnitudes gives us good reason to think that his conception of number in general is cardinal, and hence that his conception of number includes both cardinal and ordinal elements, with the latter making the exact representation of particular cardinals possible. I should say as well that I'm thinking this is his fundamental notion of number. I'm not saying that he doesn't recognize that you can simply order things in numbers and so on, in ordinal use of grocery list or something like that. Now I want to raise a challenge to my view here. According to a modern account, the cardinal conception of number rests on the notion of same size of collections, understood as a one-to-one correspondence between the individuals of two collections. And that is explained in terms of the existence of a one-one onto function from the elements of one set to the elements of another. from a modern perspective, it might seem that any understanding of cardinality not based on one-to-one correspondence is either not a cardinal conception properly understood, or at least is too thin to be really interesting. If this were right, it would be a serious problem, for Kant, as far as I know, never even refers to one-to-one correspondence. And I think that if we approach Kant's text from our modern perspective, and we cut your teeth on Frege, the lack of any one-to-one correspondence would naturally lead one away from a cardinal interpretation. I will argue, however, that Kant has a perfectly adequate account of equinumerosity and cardinality that does not appeal to one-to-one correspondence. And we'll also answer the lingering question I left in the middle of the paper about how we get from representations of collections to representation of the size of a collection. So I'll pass over details and have to summarize here. Kant defines quantity and quality by appeal to his theory of magnitudes, and the quantity of a collection of discrete individuals is their quantitative determination insofar as they are considered as a homogeneous manifold. That is, insofar as they are considered as merely numerically distinct. This quantitative determination is the size of a collection. What is important for present purposes is that the starting point of Kant's account of cardinality is not equinumerosity or sameness of size, but size itself. That is, a collection represented under the quantitative categories of unity, plurality, and allness. Equality is then defined following philosophical addition as identity of quantity. So equinumerosity is identity of the quantitative determination of collections of discrete magnitudes. Thus, if we follow Kant's philosophical definition of equality, equinumerosity is not grounded in one-to-one correspondence among collections. As I pointed out earlier, however, the categories alone will not give us the concept of number. And one might worry about whether the categories of quantity employed in the representation of collections can even provide us with a notion of particular sizes of collections. Once again, it might seem that the categories of quantity are indeed employed in the representation of collections, but then any notion of the particular size of a collection will depend on enumeration, and so number starts with the ordinal side of it. Ordinal elements would be the key to moving from the notion of a collection to the notion of particular sizes of collections, and once again, Kant's conception of number might be solely ordinal after all. I want to suggest that in Kant's view, the quantitative determinations of small collections can be and are directly represented in intuition, so that the particular quantitative determination is the particular configuration of identity and difference of individuals in the collection. This is sort of a Kantian version of the familiar formula defining the extension underneath the concept. There exists an X, there exists a Y, such that f of X, f of Y, X is not identical to Y, and for all Z, and so on. But here, Kant is applying to numerical identity and difference, which requires intuition to represent. So the content of the representation of the freeness of three fingers, for example, rests on the representation of the mere numerical identity and difference of three individuals thought under the categories of unity, plurality, and allness. This provides a direct representation of the exact determinate size of a collection of three, and hence gives content to the concept of this particular quantitative determination. So it isn't just of a collect. I got a collection here. I got a collection of three. This is what it is to be three. And it is identity of this determination that would ground the equinumerosity of two collections of three elements. Note that we can also directly represent the part-whole relation between two of the three in the whole collection of three, and hence the ordering of these quantitative determinations. Furthermore, these representations of small collections can serve to give us the general notion of what the particular size of collections consists in. That is, a particular instantiation of identity and difference among individuals. So that's your notion of a particular size of a collection. The general notion of a particular size of a collection could be employed in a representation of large collections. The uncounted number of books on a shelf, for example. Right? So I'm thinking of it not just as a bunch of books, but I'm thinking that it's a collection that has a particular exact size. And if you take one out, then there'll be one less in that collection. If you add another book, there'll be one more. But I'm not representing what the particular number of books is. Now, more is needed. This notion of cardinality provided by the representation of very small collections is hardly robust. In fact, it doesn't even give you the notion of cardinality, properly speaking. So the sameness of size for small collections, such as 3, might be defined as the sameness of this particular quantity determination. But how are we to think of the sameness of size for larger collections? In fact, if sameness of size is not defined for arbitrarily large collections, then the notion of cardinal number will not correspond to the notion of number whose cognition Kant aims to explain, namely the notion of number underlying mathematics as well as everyday arithmetic One natural solution is that, just as enumeration in the numeral system serves to specify the exact size of a collection of arbitrary size, the sameness of size can be characterized as the sameness of the results of enumeration. But this solution presupposes that sizes of collections in equinumerosity are well behaved in various ways. For example, we think of equinumerosity as an equivalence relation. We also think that equinumerosity is stable under addition. That is, we think that if two equinumerous collections each have equinumerous collections added to them, then the results will be equinumerous. And similarly for removing equinumerous collections from two equinumerous collections. As a special case, we think that if two equinumerous collections each have one added to them or one subtracted to them, the results are equinumerous. These general properties of equinumerosity can be shown to follow from one-to-one correspondence fairly straightforwardly, but seem to be entirely lacking in Kant's case, at least so far as I've developed it. Fortunately, Kant's understanding of equinumerosity is richer than I have so far explicated, for there are general principles governing equality that support the idea that larger collections have determinate exact sizes that are related to one another in the right way. These general principles hold for the sizes of indefinitely large collections, and do so in a way that appeals neither explicitly nor implicitly to one-to-one correspondence. So I'm going to just have to summarize here and say that Kant thinks that equality and in particular equinumerosity is an equivalence relation. His views on equality as identity of quantity commit him to it, and then he also commits himself explicitly to various principles that entail it. Now that's the first step. Equinumerosity is an equivalence relation, but there's much more. In the axioms of intuition, Kant states, and this is number 14 on the handout, that equal put together with equal or taken away from it yields an equal are analytic propositions. Kant holds that there are analytic principles governing equality, namely the twin principles that equals added to equals are equal and equals subtracted from equals are equal. These actually are commonly included in Euclid's notion, are included in many versions of Euclid's elements. I will call them the equality under addition and subtraction principles, or the EAS principles. To cut a long story short, I go detour through Euclid and Kant's relationship to Euclid and his understanding of magnitudes and so on and so forth. We should understand the EAS principles governing discrete magnitudes as, and this is number 15 on the handout, just as many added to just as many are just as many, and just as many subtracted from just as many are just as many. Kant holds these principles to be analytic. Thus, the concept of sameness of size analytically contains the condition that sameness of size is preserved under addition and subtraction in the indicated way. Note that as a special case, these principles imply that if you have a just as many pair and add a disjoint individual to each, or subtract an individual from each, then the result is a just as many pair. Now consider the following principle, which I'll call the just as many as none principle. If there are no things of a particular kind, then there are just as many things of another kind, if and only if there are no things of the other kind. It seems overwhelmingly likely that Kant would think that this principle is analytic of the concept just as many. These analytic principles govern the notion of just as many, and so this is another account of equinumerosity rather than one-to-one correspondence. That's one of the reasons I called it just as many, to make that clear. And it does not appeal to one-to-one correspondence in any way. But how good is this? One might wonder how far this notion of just as many will get you. The answer is quite a bit further than you might think. As Richard Heck has shown, versions of what I call the EAS principles and the JMN principle are sufficient to fix the notion of equinumerosity in a way that makes it possible to derive the Peano axioms for finite cardinals, all without appeal to one-to-one correspondence. And I give a reference to his paper there, number 16. I think it's a wonderful, very interesting paper. Kant, of course, would not have thought of things in anything like this way. However, Kant explicitly states that on condition that they are exhibited in intuition, the EAS principles are admitted to mathematics. So he thinks that the principles do in fact play a role in arithmetical cognition. The point is that the principles fill out his notion of cardinality and do so without any appeal to one-to-one correspondence. Now, we can learn a bit more about what how Kant thinks analytic principles play a role in mathematics. The continuation on the passage of part-whole relations that I quoted earlier from B1617, that was number 12 on the handout. I repeat it in number 17 now. It continues with another sentence. So if you look at number 17, the whole is greater than the part is analytic and so on. And indeed, these themselves, even if they are valid according to mere concepts, are only admitted to mathematics because they can be represented in intuition. It is only insofar as the part-whole relations of magnitudes can be represented in intuition. I want to suggest the same thing for the EAS principles and the JMN principle. It is only insofar as the part-whole relations of magnitudes can be represented in intuition that these conceptual truths can play a role in mathematics. And through that representation in intuition, the analytic principles are supplemented in a way that makes them not just conceptual but properly mathematical. In the case of the EAS and JMN principles, that is nothing other than generating a representation of particular sizes independently of the notion of same size by representing identity and difference in intuition, something that is only possible for small collections but which is sufficient to give us a notion of exact size and same size, and does so independently of the notion of equanimity characterized by the JMN and EAS principles. It is a representation that grounds the principles and allows them to be admitted into mathematics. So here are the conclusions. We have found that the most important texts at the time of the Critique of Pure Reason are not unequivocal, but indicate that Kant's conception of number in general includes the notion of the sizes of collections whose ordering is grounded in part-whole relations. At the same time, Kant's conception includes ordinal elements for the specification of the exact size, or I should say the exact representation of the size of particular cardinal numbers. This comes out most clearly in Kant's emphasis on enumeration, which is not treated as simply a necessary condition of number representation, but is contributing to the conception of number itself. Furthermore, Kant appeals to the ordinal elements in his conception of number to explain the possibility of measurement, and hence the application of natural numbers to continuous magnitudes. Finally, we found that Kant's cardinal conception of number in general does not rest on the notion of equinumerosity understood as one-to-one correspondence, but on the direct representation of collections in intuition, together with the notion of equinumerosity governed by analytic principles. These conclusions partially vindicate both cardinal and ordinal interpretations of Kant's philosophy of arithmetic, and make the best sum of the most important text in the critical period. Kant's mixed conception of number would be viewed as defective if its primary purpose was to provide a foundation from arithmetic. I mean, of course, we're looking back as from our perspective. But Kant's aim is to explain the possibility of arithmetical cognition in terms of our more fundamental cognitive resources. In doing so, Kant shows a sensitivity to the fact that arithmetical cognition, of which humans are capable, and even the application of numerical concepts to individuals and collections, is a complex achievement that requires a sophisticated employment of our basic cognitive resources. This interpretation of Kant's conception of number will allow us to better evaluate later interpretations and assessments of Kant's account of what makes arithmetical cognition possible, from Frege to Cassirer. Cassirer has some very interesting comments on Kant in this regard, and to contemporary Kant scholarship. It will also allow us to better understand the relationship between Kant's philosophy of arithmetic and our own. Finally, it puts us in a much better position to identify and then evaluate the specific roles that Kant thinks space and time play in arithmetical cognition. Thank you.
What a rich paper. Thank you. I don't think we'll have time for all the questions, but we'll just go around the table now.
I should say I was very glad that Bill didn't have to leave the conference before my class. I always going to leave my
Well, I just wanted to point out that the number is the schema of quantitas, and there are two ways of understanding that. I always thought that preferred way was magnitude, because there are other places in the critique where he makes that distinction, and that is magnitude. Well, it's interesting because Emily translated it as quantity, and then obviously number is cardinal number. On the other hand, if it's magnitude, then where does number come in? Well, to take the magnitude of something is relative to a unit, so you're looking at the ratio of x to u, and that's defined in terms of equal multiples, and that probably is an ordinal. I would call that an ordinal notion of number. So from your translation of it, I would assume that ordinal numbers. I mean, in the context of number as the schema of quantitas. In the case of Emily's translation, I would think
Well, Kant does say.
to be cardinal number.
Okay. So, first of all, Kant does say magnitude. Well, so maybe I should be clear. Translate the text in different ways, but I think we need to be a bit more sensitive to the different vocabulary. So, right, practice was to use magnitude to translate größe and quantity to translate quantité. Okay, so that's just so given the way I think the terms should be translated, I think it should be magnitude. But I think that perhaps we have a different understanding of what magnitude means. So you immediately go from the reference to magnitude to, oh, well, there's a specification of unit and there's a ratio between them. I know we've talked about this, and of course, one thing is completely alike in this article is the important connection between Kant's arithmetic and the algebra and the theory of proportions, which I've written about elsewhere, and I just had to drop that out. But my understanding of Kant's understanding of magnitude, the magnitude is, as he defines it, which is a homogeneous manifold of any intuition in general, insofar as it makes a representation of an object possible. Okay, there's no reference to a ratio in the definition of magnitude. So it's, I think, the notion of magnitude that you're appealing to here is leading too directly to the theory of proportions, which Kant definitely has in mind. But what he means by magnitude, and he's absolutely explicit about it, when it's playing the crucial role in the axis of intuition, is that it's a homogeneous manifold in intuition. So I think that the fact that he's using the word größe there, or magnitude, as I would like to translate it, doesn't simply indicate all by itself that you must have an ordinal conception. And I actually want to just add that I don't see why translating as quantity would push you toward a cardinal interpretation either. I took it as umgekehrt. I thought that well, no, one has to be careful here. So I'll just leave it at that.
Yeah, would you want to say that one of the conceptions is more fundamental than the other, or there's a dependence relation? So the cardinal conception depends in one direction on the ordinal conception, or flipping around the other way. The reason I ask is because it seems like you could you would want to say that if you think of cardinals as like invariants through different orderings. So then it seems like you might want to say that ordinals are, in some sense, fundamental, and you get cardinals through something like abstraction. So there's a kind of cognitive process involved in cardinal awareness that's not involved in ordinal awareness, and that might suggest a dependence relation. But maybe that both are involved. That is, you have both cardinal and ordinal conception, but that's some kind of cognitive activities involved in the one case. And I don't know whether you want to flip it around the other way and argue that, since you argue that cardinal conception is generally the one, whether you would want to say ordinals are somehow dependent on, are founded on cardinals.
Okay, so that's very interesting. So I do come to say Kant's conception of number in general is cardinal, and then Kant's conception of number in general is cardinal. but that ordinal is not simply a necessary. The ordinal elements aren't simply necessary; they're included in the conception itself. So I was trying to give them equal status in a certain respect, but there is a way in which, because the general concept of number is cardinal, I wanted to say it was more fundamental. But I also think that I probably am still under the influence of my reading of the theory of magnitudes, and you guys are going to slip my throat afterwards? I'm getting a little worried. In light of the sort of considerations I think Emily was bringing out in her paper, I think that the representation of cardinals is in a very important way, or of collections, and it is in a very important way more fundamental in that respect as well. Now, I don't know that Kant in any way, where any place reflects on the fact that you can order, does he? That the cardinal number is invariant under orderings, different orderings. If he did say that, that would be very interesting, but I don't know that he does. And I appreciated it. I mean, you were pointing out last night when we were talking that even before some of the initial progress in the foundations of arithmetic, Kant gave that the issue of cardinal versus ordinal conception of number was a live issue, but attached more in the sense that I have been pressing here in an account of arithmetical cognition, and specifically that relation. So that seems to me a very interesting development, and I don't see Kant reflecting on that. But there is another worry here, and that is, well, okay, so I did say at one point, I'm not denying that Kant doesn't think that you can use ordinals to order things and do lists. So we might think, well, but is that dependent on cardinal conceptual number or not? And I don't think so. But what I was inclined to say before, and I think I'm still inclined to say it, was that the notion of an ordinal number as number was so little developed in Kant's time, it would have been thought to be not sufficient on its own to support a full conception of number. And I think they're very, so the thinness of Kant's ordinal number, but also the way ordinals are applied in ordering things, where the ordering itself is important, but you might think the number isn't important. I think there are various considerations that would push in that direction, but that's what I would like to say.
We're going to have just one very short and then two additional questions, and that's it.
Yeah, I just want to speak to that question. I think if you want to get from cardinality may be seen as the invariance through different orderings to the conclusion that the cardinal conception depends on the ordinal conception, you will need an additional premise, namely that is the only way to think of cardinality.
I just wanted to ask a question. Does Kant have anything to say about finite cardinals or finite ordinals or infinite, I should say? Infinite.
Infinite. Well, yes. Yeah, the short answer is no. Not in the, yeah. No.
Because it looks to me as though he would be committed, implicitly at any rate, not to have them.
He's committed
Yeah,
to
he is
number
committed.
only applying to finite.
That's right.
Number can't be.
Yes, he is committed to this. Yeah. All right.
And over.
I don't want, you ended by saying that the analysis is instructive for thinking about other things, like how, well, like I'm tired, like the role of intuition.
Yeah.
Now, here you bring up these, Kant always brings up the principles that are said to be analytic are the only places where he brings in inequalities. He never seems in any, I haven't seen it in any text, an inequality in numerals. Well, there is this comment that he makes, well, that we ought to think the addition of the two in one number. Oh, that's maybe in the letter to Schultz. That we ought to think that there is something that there is something that is the sum of the two numbers is not to the point. The question is whether. But I wonder whether the analysis that you've just given is helpful in thinking on why he would be. Avoiding inequalities might have to do with something having to do with more general principles. In particular, ones that do have to do with time. So I conjecture at some point that it might have to do with avoiding commitment to the principle of dichotomy or time. So, but that may not have anything to do with what you would think.
There's an inequality at this 16, 17. It's number 17. A plus B is greater than.
Right, that's analytic. So it's just so inequalities only come in these they never have inequality in numerals. It's always no synthetic example of an arithmetical integral.
Okay, I think.
No, that's very interesting.
Well, you'll have all of lunch to think about it.
How long is lunch for you?
And lunch is until 2:30. We will reconvene at 2:30.